Every AI system you've heard of in the last 5 years, ChatGPT, image generators, voice assistants, recommendation algorithms, runs on the same basic structure underneath. It's called a neural network. And despite the name, it has almost nothing to do with the brain. The name is a historical accident. The concept is mathematical. And once you understand what a neural network actually is, not the biology metaphor, but the real mechanism, you'll have the foundation for understanding nearly everything else about modern AI. Let's start from scratch. A neural network is, at its core, a function. You put numbers in, you get numbers out. The interesting question is what happens in between, and how the network learns to produce useful outputs. The basic building block is called a neuron, or more precisely, a node. Each node takes in some numbers, multiplies each one by a weight, adds them all up, and passes the result through a simple mathematical function. That's it. One node does almost nothing interesting, but stack millions of them together, organized into layers, and something powerful emerges. Here's the architecture. Numbers flow in at the input layer. Pixels from an image, tokens from a sentence, sensor readings from a device. They pass through one or more hidden layers, where each node performs its weighted sum and activation. Then the final numbers come out at the output layer. A predicted category, a generated word, a score. The word deep in deep learning just means there are many hidden layers between input and output. More layers means the network can learn more abstract patterns. The first layer might detect edges in an image. The next might detect shapes. Further in, faces. Further still, identities. Nobody programmed those concepts explicitly. They emerged from the weights. There's one more ingredient worth naming, the activation function. After each node computes its weighted sum, it passes the result through a simple non-linear function before sending it to the next layer. Without this step, stacking layers would be mathematically equivalent to having just one layer, no matter how many you added. The non-linearity is what lets deep networks represent genuinely complex, curved relationships in data, rather than just lines and planes. It sounds like a technical detail. It's actually what makes depth useful at all. And that brings us to the key question. Where do the weights come from? This is training. You start with a network where all the weights are random, essentially a function that produces gibberish. Then you show it examples. For each example, you run the input through the network, compare the output to the correct answer, measure how wrong it was, and then adjust every weight in the network very slightly to make it a little less wrong. Do that millions of times across millions of examples, and the weights gradually shift into values that produce useful outputs. The network hasn't been told any rules. It has found patterns in data, encoded as numbers in its weights. The adjustment process is called backpropagation, and the measurement of wrongness is called the loss. Minimizing the loss across all training examples is the entire goal of training. The optimizer, often a variant of gradient descent, figures out which direction to nudge each weight to reduce that loss. Think of it this way. Imagine you're lost in a hilly landscape and you want to reach the lowest valley. You can't see the whole map. All you can do is feel which direction slopes downward and take a small step that way. Gradient descent does exactly that, but in a space with billions of dimensions, one for each weight in the network. This sounds abstract. Here's what it means in practice. A network trained to classify images of cats versus dogs doesn't contain a rule that says, look for pointed ears. It contains billions of weights, adjusted over millions of training examples, that collectively implement something far more sophisticated than any rule a human could write. The behavior is real. The reasoning is opaque. The amount of training data required scales with the complexity of what you're asking the network to learn. A network that needs to recognize 10 categories of images might train on tens of thousands of examples. A language model that needs to understand and generate human text across thousands of topics trains on hundreds of billions of words, essentially a significant fraction of the written internet. The weights don't store those words. They store the statistical patterns across them, compressed into numbers. The data shapes the model the way experience shapes a person, except there's no understanding behind it, only correlation. The size of a network is measured in parameters. A parameter is just a weight, a single number in the network that gets adjusted during training. Early neural networks had thousands of parameters. Modern large language models have hundreds of billions. More parameters means the network can store more patterns, represent more complex relationships, and generalize better across a wider range of inputs. But it also means more computation, more memory, more training data, and more energy to run. Size is not free. There are also architectural differences that matter enormously. The networks behind image recognition are structured differently from the ones behind language models. Convolutional networks process spatial patterns efficiently. They're designed for grids of pixels, applying the same set of weights across different positions in the image. Transformers, which power modern language models, are designed to process sequences and capture long-range relationships between tokens. Any word can directly influence any other word, no matter how far apart they are in the text. The architecture is not a cosmetic choice. It determines what kinds of patterns the network can efficiently represent, and therefore what it's capable of learning at all. It's also worth noting that not every neural network is a large language model. The same basic architecture, nodes, weights, layers, training, underlies spam filters, fraud detection systems, medical image analysis, self-driving car perception, and protein structure prediction. The applications look completely different. The foundation is the same. What changes is the architecture, the training data, the objective, and the scale. Understanding neural networks is not understanding one technology, it's understanding the substrate of almost everything in modern AI. One thing worth understanding, despite all of this capability, neural networks don't understand anything. They find patterns. They encode statistical regularities from training data into weights. When a network correctly identifies a photo of a cat, it isn't applying any concept of cat. It is performing a computation whose output, after training, happens to correlate with what humans label as cats. This distinction sounds philosophical, but it has practical consequences. Networks fail in ways that nothing with genuine understanding ever would. They can be fooled by tiny deliberate changes to an image, imperceptible to humans, catastrophic for the model. They can be confidently wrong on inputs that look nothing like their training data. They can learn spurious correlations from biased datasets. These aren't edge cases, they're structural properties of how the approach works. Understanding this doesn't diminish what neural networks can do. What they can do is extraordinary, but it does clarify what they actually are. Very powerful, very flexible pattern matching functions trained on data, with no understanding of the world behind the outputs. Here's the mental model worth keeping. A neural network is a function defined by its weights. Training is the process of finding good weights. Everything else, the biological metaphors, the science fiction associations, the hype, is noise around that core idea. Every AI capability you've seen or read about sits on top of this foundation. The differences between systems come down to architecture, scale, training data, and fine-tuning. None of that complexity changes what the underlying object is, a mathematical function that learned to be useful by being wrong a very large number of times. When you understand the foundation, the rest of the field starts to make sense. And that's what this channel is here for. If this kind of clear mental model is what you're looking for, subscribing is how you get the next one.